Guys, this is geometry. We're going to learn topic 5 now, relationships and triangles. In this topic, we'll think about how the sides, segments, and angles of triangles are related. So, just overviewing our topic, we have 5 lessons total in this topic, and these are some topic vocabularies that we're going to look at later. Altitude, centroid, circumcenter, circumscribe, concurrent, equidistant, incenter, inscribed, median, orthocenter, point of concurrency. So we'll talk a lot about triangles and circles additionally. Okay, are you ready? Let's go to lesson 1. Also, before we learn about jump into lesson 1, did you know that an object's center of mass is the single point at which its mass is evenly dispersed and the object is in balance? If the center of mass is too forward, the plane's going to go downwards. And if it's too far back, the airplane's going to lose stability. You can't really control the direction. So the center of mass needs to be in the center. And that's very important when we're flying in an airplane. So we'll think about we'll think a lot about the center of mass in this topic as well. And this is just only one example that we use the concept of geometry in real life. Okay, in lesson 1 of topic 5, perpendicular and angle bisectors, we'll be able to use perpendicular and angle bisectors to solve problems. You already know that the midpoint of a segment is equidistant from its endpoints. So in this lesson, you'll learn how to find other points with this property. In addition, you'll also learn about points that are equidistant from the sides of an angle. So the vocabulary equidistant is very important. It means the same distance. So it just means that the 2 points are going to be the same distance away. Okay, a new high school will be built for Brighton and Springfield in Model and Discuss. The location of the school must be the same distance from middle school. The distance between the 2 middle schools is 18 miles. Okay, so we got Brighton Middle School on the left, Springfield Middle School on the right, and we want to think about the distances. So part A, trace the points for the schools on a piece of paper. Locate a new point that is 12 miles from each school. Compare your point with the points of other students. Is there more than one location for the new high school? Okay. I've just copied the graph down that have Springfield Middle School here and Brighton Middle School here. And the distance between them is 18 miles. And so I am supposed to locate a new point where it is 12 miles from each school. So I said, oh, this is 18 miles. Yeah, the distance between is 18 miles. And so the half distance would be about 9. And so 12 would be like, it's going to be about maybe 75%, 3/4. And then I estimated it. So this could be 12 miles, that could be 12 miles, but it needs to be 12 miles away from both middle school. Right. So So I chose a point below, but if you compare yours with mine, you might have a point above them, or you might have, you might have a point the same as mine, but it should be about the same. It should be about here or here, because it needs to be 12 miles away from the school. And so the distance from each point doesn't change, right? So from here, you're gonna actually, you can use a compass to draw a circle, an arc. And then here, you can draw another arc using a compass that's equidistant. And then there's gonna be a point where both arcs meet, where both circles meet, but there could be 2 points, both above and below. So that's what we're going to explore in this lesson. So let's look at part B. Can you find locations for the new high school that are the same distance from each middle school for any given distance? So like we said, wherever the point is, if you want to find the same distance, you can draw a circle with the same radius without changing the distance, so that you can see where the points meet. And that could be the points where it's equidistant from whatever points we're starting with. So why don't we write that down? Okay, so part A, I said, oh, there's gonna be a midpoint where it's 9 miles away from both middle schools, right? And so that could be, because the distance from each middle school would be 18 miles. But there could be 2 points. Wait. But there could be 2 points. Okay, that's not a good circle, but there are going to be 2 points above or below, maybe like here or here. That's 12 miles away from each school. Okay, that was part A. Let's write part B. Okay. Yes, we can find locations for the new high school that are the same distance from each middle school for any given distance, because we can find a midpoint and then place other points above or below using compass or ruler. All right, so let's think about this questions. What is the relationship between a segment and the points on its perpendicular bisector, between an angle and the points on its bisector? Example 1, find equidistant points. How can you find points that are equidistant from the endpoints of line AB? What do you notice about these points and their relationship with line AB? Vocabulary word here. A point that is the same distance from 2 points is equidistant from the points. Same distance. Okay. So how can we draw? How can we figure out using construction? So if you have a line AB where you have 2 endpoints A and B, you can use a compass to draw intersecting pairs of arcs centered at A and B. The points where the arcs intersect should be equidistant because you didn't change the compass setting, or rather you shouldn't, right? So they are the same distance away, they are the same distance away, right? And then the 4 points appear to be collinear. if you notice that all the points that are equidistant from A and B tends to be collinear on the same line. You can draw a line L through the points to say, oh, all the points on this line will be equidistant from the 2 points. And think about the common error here. Make sure not to change the compass setting when drawing each pair of intersecting arcs from each endpoint. Why? Because if you change it, that means it's not equal distance. It needs to be equal distance. Okay, so the points that are equidistant from A and B appear to lie on line L. Line L appears to bisect the and be perpendicular to line AB. How special is that? You can use a ruler and a protractor to support this hypothesis. So we have a hypothesis now. All the points that are equidistant from the 2 endpoints to any 2 points make a line L where the line bisects and is perpendicular to the line of the 2 points. Isn't that amazing? Beautiful. Let's look at try it. Number 1, draw a pair of fixed points and find points that are equidistant from the 2 fixed points. Draw a line through a set of equidistant points. Repeat this process for several pairs of fixed points. What conjecture can you make about points that are the same distance from a given pair of points? Basically, you do the same thing that we looked at in example 1 over and over again for any 2 random fixed points. And you will figure out that this hypothesis holds true. Just like we looked at in the previous problem, right? To middle school, 18 miles away, find the middle point, 9 miles, and then draw a point that has the same distance, could be either below or above, but all the points actually have to lie on the same line as the midpoint. Isn't that amazing? Yeah, if you draw any 2 random points and do the same thing, you will end up with a line that bisects and is perpendicular to the line of the 2 points. So let's write that down. Okay, so let's write down the amazing discovery we figured out when we have at least 2 distinct pairs of fixed points. The points don't move. All the points that are equidistant from the 2 fixed points lie on the perpendicular bisector of the segment joining the 2 points. That was example 1, discovery. Theorem 5.1, here we go. Perpendicular bisector theorem. Ta-da. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Okay, so in this diagram, if we have a line xy, then a point P equidistant from x and y lies on the line that is a perpendicular bisector of the line xy. Theorem 5.2, converse of the perpendicular bisector theorem. So you flip it around. If a point is equidistant from the endpoints of a segment, then that means it is on the perpendicular bisector of this segment. Okay, so if xq equals yq, so if they're equal and you know q is a midpoint, then PQ is a perpendicular bisector of XY. I think that's supposed to be XP equals YP, right? If a point is equidistant from the endpoints of a segment. So yeah, it's xp equals yp. All right, example 2, prove the perpendicular bisector theorem. Okay, we're gonna prove using the logics that we've already set so far as a foundation. So proving perpendicular bisector theorem. Given L, line L is a perpendicular bisector of xy, we're going to prove that px and py is equal, which means p is in this is equidistant from both points. Okay, so the proof starts with knowing that all right triangles are congruent. So we know that all the angles, corresponding angles, and the corresponding sides, all the parts would be congruent. So we can say, oh, then XQP and YQP are right angles, so they're going to be the same. But a reflexive property, oh wait, right angle, yeah. So all the angles are going to be the same. So they're congruent, but a reflexive property, this PQ is equal to itself. And since L is perpendicular bisector of XY, you know Q is going to be equidistant from X and Y. So we have two sides, two corresponding sides of those two half triangles are going to be congruent. And one included angle would be congruent. So we have SAS theorem to prove that the two triangles are congruent. And then by CP/CTC, we can say that PX and PY are corresponding sides and they should be congruent. Okay, so in try number 2, we're going to prove the converse of the perpendicular bisector theorem, where we have given px equals py. That's our given, and we're going to go backwards. We want to prove that L is perpendicular bisector of xy, right? Yeah, so the converse is always going to be switched. How do we start? First, you always start by writing out the given and your goal, proving. So given px is equal to py. Prove what? PQ, line PQ is perpendicular bisector of xy, line xy. So, and now our plan is that we state the given information. What can we say from the given information? Because px and py are congruent, pxy, the whole triangle, is an isosceles triangle. Can we say that? Yeah, from the given information, we can say that. So let's start with that. Given px is equal to py, triangle pxy is isosceles. And now we can use the definition of isosceles and the theorem, isosceles triangle theorem, right? So what does the isosceles triangle theorem say? If the triangle is isosceles, you have two sides that are congruent and two angles that are congruent. Two angles that correspond to the angle on the base, right? So we can say that pxy and pyx would be congruent, okay? By the isosceles triangle theorem, angle pxy is congruent to angle pyx. Since every segment has a midpoint, you can draw a midpoint Q and XY. And from the definition of midpoint, XQ and YQ should be congruent. Why are we doing the midpoint? So that we can say, we can eventually go to line L using point Q, okay? We need to cut the triangle in half anyway. So this is cutting the triangle in half finally. So we can say since every segment has a midpoint, we can draw a midpoint Q on XY. So remember, this diagram is for example 2. We're just given a point PX is equidistant to PY. Okay, that's what we're given. And we just want to prove that PQ is perpendicular bisector of XY, where Q is the midpoint. Okay, so we can draw midpoint Q on XY. We just set that definition in there. Q is going to be the midpoint. And by definition of midpoint, XQ should be congruent to QY. And then what do? We have that these two sides are congruent, that's given. And then the angles are congruent here. And then the corresponding side, another one here, is congruent. So we can cut that in half and say, oh, we have two triangles that are congruent by SAS theorem. So by SAS, triangle PXQ is congruent to triangle PYQ. And by CPCTC, angle PQX is congruent to angle PQY. Why do we need that? So that we can say, using theorem 1.5, where you have the right angle, if they're the same and they are adjacent angles, they're gonna be the right angle, right? So that is the theorem 1.5. By theorem 1.5, measure of angle PQX and PQY would be 90 degrees and it's a right triangle. So now we can say line PQ is perpendicular line XY by definition of perpendicular lines. And so now we have proven that PQ is perpendicular bisector of XY. Just state that PQ is perpendicular bisector of X. Okay, that was very similar to our example 2 proof, but we have gone backwards. We used the same SAS, but we had to use a lot of definitions and the old theorems. All right, let's look at the next example. Now we'll be able to use a perpendicular bisector. Mr. Lee wants to park his ice cream cart on Main Street so that he is equidistant from the entrances of the amusement park and the zoo. Okay, where should Mr. Lee park? How can he determine where to park? He wants to, basically find a point where it is equidistant from the entrance of the amusement park. Okay, that's the entrance. And then the zoo. So pick the 2 points, plot the 2 points, and that's gonna be the shortest distance and the line between those 2 points. Where should he park? So you can basically draw a perpendicular bisector and say, oh, he can park anywhere on this line, but you can see on the map that this area above the line would be forest, and I don't think that's a parking area, so he can park anywhere here. Okay, So he can use a perpendicular bisector of the segment, connects the two entrances to find the location. So do we have a set distance? Yeah, so it could be anywhere on this line, but on the parking lot. He should park his car at point T. So pick a point T because it's equidistant from both entrances. Oh, wait. I guess we can't park it on the ground, like the brown area, because that's part of the the pedestrian road. So he can park on the road where like the side of the road where he meets the point. Okay, that makes sense. Try number 3. The entrances are 40 feet apart. Mr. Lee decides to move his cart off the street to the area between Main Street and the entrances to the amusement park and the zoo in the Main Street. Okay, here, Main Street. How can you find where Mr. Lee should park if he must be 30 feet away from both entrances? So basically do the same thing, construct a perpendicular bisector of AZ, and then label the midpoint here as point M, and then AZ, yeah, and then MA, you find the midpoint of MA, you can call that a P, and then MP, midpoint to point P, where he could park, has to be 10, so that from point P to Z is 30. Do we have more information? Yeah. So basically you can draw an arc that is equivalent to 30 feet from both entrances, and you're gonna find a point, the intersecting point. And that's gonna be where he should park. Oh, I see, yeah. The entrances are 40 feet apart. So you know that these two points would make 40 feet. And then you can find another midpoint here and say, oh, this is going to be 20 feet apart, and that's going to be 10 feet apart. And we can just multiply this distance of 10 feet by 3. And then we can say, oh, I'm gonna, so use the compass to measure this point M here, and then point M to A, and that's gonna be 10 feet. And then you're gonna draw an arc. And then from any distance, any point here, you're going to draw another arc that's the same settings. And so you're going to draw a straight line so that you don't change the direction. And then you draw another arc from the third point. And that should give you 30 feet, right? So if you draw 3 circles starting from point A, but you're going to measure point M here. And then you draw the first circle and then pick just any point. And then you're going to draw another circle, and then now it needs to be straight from point A to another point P here. And then you keep doing that, and then once you hit here, that's going to be 30 feet apart from point A. And use the compass to stretch and measure that, and then draw a big arc representing the 30 Okay, this is all going to be 30 feet away. And then using the same setting, you can do another arc from point Z, because that also represents 30 feet away from point Z. And then wherever the arcs meet would be the intersecting point where he should park. So let's write that down. First, you're going to construct the perpendicular bisector of line AZ. Or you know what's better? After you find the midpoint of ZA, and then you find the midpoint of MA. So if this is M, and you find the midpoint here, and that is a P, that's going to be 10, and this is going to be 20 feet. So together from Z to P, that's going to be 30 already. You don't need to do the whole 3 arc thing. Okay, so that's 30 already. So you can directly choose that measure Z to P, and then draw arcs from Z and A, centered around Z and A. Okay, so after you find the midpoint of ZA, which is M, find the midpoint of MA, which is P. MP is 10, so ZP has to be 30. So you're going to measure that and construct circle center around Z and A. And the point of intersection is where he should park his car. Done. Okay. Some errors, common errors that you might have is that you may locate the points 30 feet from the midpoint of AZ instead of 30 feet from either entrance. So he wants to be the same distance from both entrances. It needs to be represented by points Z and A, not 30 feet from the midpoint. So you can't measure it from the midpoint here. You have to, don't draw an arc from the midpoint. You have to draw 2 arcs from center around Z and A, and then the intersection point would be where he could bike. All right, last example, I believe. Wait, no, I lied. Third to last example. Why don't we stop here for this video, and then take a little break. We'll come back. You can come back after when you're ready.